Hi, welcome back. And we're going to move on into our next segment of doing our thermochemistry calculations. And we're going to look this time, instead of phase changes, at enthalpy changes in chemical reactions. Now, in a chemical reaction, just as a quick refresher, remember for exothermic reactions, heat is listed as a product because it's formed or exiting the system. Delta H is negative. For endothermic, it's listed as a reactant. Endo, entering, exo, exiting. Okay, so that's kind of a play on words there, trying to help you out. Delta H would be positive. All right, and so when you're looking for these in a chemical reaction, here you notice that we see energy as the product. Here we see energy as a reactant. So this one is exothermic and this one is endothermic. Okay. Now, when we write those, it's hard to write. Do you notice it doesn't say per mole? Sometimes you'll hear people talk about it as per mole of reaction. That was a pretty big conversation in AP chemistry. And what they're meaning by per mole of reaction is when the reaction is balanced like this, that means I'm going to release that amount of energy for every 1 mole of this, for every 5 moles of oxygen, for every 3 moles of CO2, and for every 4 moles of H2O that are formed. In this reaction, for every 1 mole of nitrogen that I react, or every 1 mole of oxygen that I react, remember what it would be depending on is what is the limiting, right? What is my limiting reactant would dictate it. And I'm going to require that much energy if I wanted to form 2 moles of NO. So you see, we get a series of conversion factors that can be used when we are given the heat, the enthalpy change of a reaction. So all these are doing, and I think that's the difficult part. I say all these are doing. I think the tough part of this unit is kind of knowing when to use which calculation. So let's take a look at this one here. We know what to do because A, we have a reaction, and B, we're given the value of the energy inside the reaction. So this asks us, I've got 5.66 grams of carbon disulfide. So I'm going to do a dimensional analysis. Whenever you have the enthalpy, even when you have the enthalpy of fusion, the enthalpy of vaporization, the enthalpy of a reaction, they really do all kind of boil down to, so to speak, a dimensional analysis. So that might help you out a little bit there. So I'm going to start with my 5.66 grams. Now, this is kilojoules per 1 mole of carbon disulfide. So I need to get from mass to moles. Mass to moles, use molar mass, 76.14 grams. Now I'm going to use this value. It's a positive, I'm not multiplying, but the value is positive. Or excuse me, I'm not adding, the value is positive. We're multiplying by a positive value. Sorry, I didn't make that clear at all. Kilojoules per, look for that coefficient, 1 mole of CS2. So remember, we multiply each of these. I was just trying to emphasize here that it's going to be a positive value. So it ends up being plus 6.64 kilojoules. Okay. Now on this next time, it's asking us about sulfur. So again, I have an enthalpy. And when I have an enthalpy, you're going to do a dimensional analysis. I need to go mass to moles, then moles to kilojoules. So I've got 16.83 grams of sulfur. Mass to moles, use molar mass. We're going to assume that it's, just the S. So, and that's 32.06 grams of sulfur per 1 mole of sulfur. Now, this time it's that many kilojoules, and remember it's going to be positive, 89.3 kilojoules, but this time it's for every 2 moles of sulfur that are reacted. So I would get a positive 23.44 kilojoules of energy would be, since these are positive, that amount of energy is required. Now, do you notice it just said energy change? What was the amount of heat change? And that's because we want you to figure out whether it's required or released. Okay, so those are words we want you to start to wrap your mind around. Okay, let's take a look at another example of these. 2 more quick examples. Okay, so this time we have production. Okay, we've got iron 3 oxide, right? And we're going to have some steps. That may be too many, but I just wanted to go ahead and be ready. Now, I've got iron 3 oxide and carbon monoxide. Do you notice it says the enthalpy is negative? So that means that the heat would go on the product side, if I could write it right, plus 26.3 kilojoules as a product. So I have excess. It's not a limiting this time. It could be a limiting. It's expected that you know how to do a limiting reactant problem now. To figure out the energy, you'd have to first figure out which was your limiting reactant and then do this dimensional analysis with the moles. So I have 3.40 grams of carbon monoxide. I want to get rid of grams and go to moles of carbon monoxide. And that molar mass for carbon monoxide is 28.01 grams. And now this tells me I'm going to release. I'm going to put that little negative sign up there as a reminder that I'm releasing energy because it's exothermic. The heat was a product. And it's kilojoules per, look to your stoichiometry, 3 moles of CO. And I didn't need that last part of the line. And you should get minus 1.06 kilojoules. Okay. And then we'll look at the thermite reaction. And in this case, we have a delta H that's negative, and my AP kids are begging me to set this up. I've never done this reaction. So after the AP test, they're begging me to set it up. I'm going to set it up. I'm excited. I hope you are, because it's pretty cool. And so since that's negative, that means our heat, is that many kilojoules. Release, that's a decimal place. So I have 25.00 grams of aluminum. I have excess, which means I don't need to worry about my iron oxide. I'm going to convert grams of aluminum to moles of aluminum. I hope you see that this is same old stuff. 26.98 grams times 9.0 kilojoules per, look at the aluminum, 2 moles of aluminum. And what I like to do here, and I recommend you find some sort of method to help yourself out. I want my little reminder that energy is released. And it ends up being negative 786.7 kilojoules of energy. Okay, we're going to look in the next segment about really how scientists determine the caloric value in food products. So until then, this is your best beloved chem teacher signing off.